Okay, let's just dive right in. We're taking this circle, something you literally see every single day in the natural world, and we're going to uncover its strict, hidden mathematical secrets. Welcome to today's Explainer. We're breaking down a really fundamental chapter in geometry today. We're going to figure out exactly how circles work, why they behave the way they do, and how just a few simple rules govern the whole shebang, from a bicycle wheel all the way up to the cosmos.
So here is our roadmap for today. We're hitting 1. Circles in the wild, 2. Defining the perfect circle, 3. Anatomy of a circle, 4. Connecting the dots, 5. Secrets of the chord, and finally, 6. The concyclicity puzzle.
All right, Section 1, Circles in the Wild, Finding Geometry in Nature.
Let's start with the obvious, right? Humanity has always been totally mesmerized by shapes, and nature naturally forms circles effortlessly. I mean, long before anyone was using compasses or graphing calculators, early humans were observing this stuff. We've even found geometric patterns in the ancient cave paintings of Gudahandi and Odisha. From the expanding ripples of raindrops hitting a puddle, to the rings hidden inside a tree trunk, to the incredibly complex, precise pattern of a sunflower, the circle is kind of like nature's ultimate blueprint.
But here's what's absolutely wild. These circular rules, they scale all the way up. Look up at the full moon, or the sun during a total solar eclipse. The exact same shape governing a tiny cross-section of a plant stem is the same shape governing massive glowing spheres in our solar system, which really begs the question, what properties actually tie all these things together? Moving on to Section 2, Defining the Perfect Circle, from Observation to Math.
So what is it? What unifies all these different things into one mathematically rigorous shape? Well, the crucial point is that a circle isn't just round. In math, a circle is a really precise collection of points on a flat plane. Think of it like a strict VIP club, where a specific condition has to be perfectly met. Every single point on the edge has to be the exact same distance from one single center point. We call this a locus of points. If even one point is just a millimeter closer or further away, boom, it's no longer a perfect circle. Okay, Section 3. Anatomy of a circle. Let's break down the shape.
So there are 4 fundamental building blocks we're going to use to unlock these hidden rules: center, radius, chord, and diameter. We already know the center is our anchor. The radius is that fixed, unyielding distance from the center to the edge. But those next two, the chord and the diameter, that is where the geometry gets super interesting.
You have to notice the subtle difference here. If you just pick any 2 random points on the edge of a circle and draw a straight line between them, congrats, you've got a chord. But a diameter, that's the ultimate chord. It's a chord that just happens to pass directly through the absolute center. And because it cuts across the widest possible part of the circle, your diameter is always going to be the longest possible chord you can draw. Picture doing this simple paper folding trick. Cut out a perfect circle, fold it completely in half so the edges overlap, and open it up. That single crease down the middle isn't random. It's a line of perfect reflection symmetry, and by definition, that crease is a diameter. Now, fold it again from a different angle. You get another diameter. And where those 2 creases cross, nailed it, that's precisely your center point. It's just a really cool physical demonstration of these strict rules. Section 4. Connecting the dots. Let's build some circles from points. I want you to try a quick thought experiment. If I give you just 2 points, let's call them point A and point B, just floating there on a blank piece of paper, how many unique circles do you think you could possibly draw that perfectly hit both of those exact points? Take a guess. Is it just 1? Maybe 2? Surprisingly, the answer is literally infinite. No way, right? But there's a catch. The centers of all those infinite circles can't just be placed willy-nilly. If a circle hits both A and B, its center has to be equally far from A and B. So all those center points form a perfectly straight line directly down the middle, which we call the perpendicular bisector. Meaning, you can draw endless circles through those 2 dots as long as you stick your compass needle somewhere on that invisible dividing line.
Next up, Section 5, Secrets of the Chord, Uncovering Hidden Rules.
Now that we know how to build them, let's uncover the elegant symmetries hiding inside the chords themselves. Take a look at a typical bicycle wheel. A simple thread tied across the spokes instantly forms a perfect isosceles triangle with the center hub. Think of that string as your chord. If you draw invisible lines from the hub out to both ends of that thread, well, those are radii, and since all radii are equal, your triangle automatically has 2 equal sides.
As the wheel spins, that whole triangle structure holds perfectly firm. And this leads us to a seriously magnificent geometric truth. This isn't just something to cram for a test. It's a guaranteed symmetry of the universe, outlined in our chapter as Theorem 5. It dictates that if you drop a line straight down from the center at exactly a 90-degree angle to any chord, it will always, and I mean always, chop that chord into two perfectly equal halves. You can literally rely on this rule to build engines, design skyscrapers, or even map the stars.
Finally, Section 6, the Concyclicity puzzle, going beyond 3 points.
So, any 3 random points in the universe that aren't in a straight line can have a circle drawn perfectly through them. But when 4 or more points manage to perfectly align on a single circular boundary, we give them a special name. We call them concyclic points. It's a real geometric rarity. Getting 4 distinct corners to perfectly trace the arc of one circle requires incredibly strict internal angles and precise dimensions.
So I'm going to leave you with this puzzle straight from the chapter to chew on. Imagine taking a rigid rectangle, which is really just 4 concyclic points forming sharp 90-degree corners, and locking it perfectly inside a circle. If you draw an X by connecting the opposite corners with diagonal lines, where exactly does that intersection land? Think about everything we just talked about concerning symmetry, diameters, and finding the perfect center. How does the rigid shape of a rectangle interact with the perfect symmetry of our circle? Ponder that puzzle for a bit, and I'll catch you in the next explainer.